It is unlikely that the Tesla switch has anything to do with Tesla. It probably comes from Carlos Benitez, but will always be known as the Tesla switch in the same way that Einstein is most famous for the E=mc² equation, which was actually produced years earlier by Oliver Heaviside. The Benitez circuit is shown here. It's an arrangement where two batteries in series are used to discharge through a load to two batteries in parallel. The version that Benitez shows has got an additional charging device here in the circuit. This is a self-oscillating mechanical device which generates, by the step up in the turns between the two sections, high voltage, high frequency pulses in a long stream, and they're fed back to both the batteries and to the load continuously as the circuit runs. The system used is often referred to as the 12 volt charges 24 volt charges 12 volt arrangement. But a major difference is that the spike generator feeds a rapid high voltage train of spikes to both the load and every battery all the time that the circuit is operating. The Electrodyne Corporation staff in America tested the following circuit here, shown in the Manual of Free Energy Devices and Systems, published in 1986. They worked on the circuit for a period of 3 years. They found that after a while their test batteries charged up to much higher than the rated 12 volts, typically around 36 volts, and they showed a much higher capacity for holding charge. They found that it could power a 30 horsepower motor indefinitely. But when you look at this circuit, which has only got 4 batteries, 4 diodes, 2 capacitors and a diode bridge, that it's not nearly as straightforward and simple as it appears to be. The batteries started out life as ordinary car batteries, but now they're 36 volt batteries with much higher amp hour capabilities. Capacitors convert cold electricity into hot electricity, so hot electricity is fed through the diode bridge to the load. As the switching used by the device was a mechanical arrangement, which has 6 switches, where 3 are on and 3 are off at any moment, the Electrodyne Corporation staff present the circuit diagram like this. You got the 4 batteries, 4 diodes which appear to be the wrong way around, and half a dozen switches which operate as 2 groups of 3, the 2 ordinary capacitors, ordinary diode bridge, and the load. The switching arrangement that they used was like this. They had a disc, a rotating disc, separated into 60-degree sections, and the middle 3 of those sections is faced in a conducting copper, and that conducting copper is used to short between pairs of isolated switches which are alternatively on and off due to the insulating green shown area. The discs are spun by a motor, and the motor has a speed control, and that's used to control the speed of the entire operation. It's recommended that this simple looking circuit has an inductive load, preferably a motor, but consider the results of that very extended period of testing. If the switching rate and switching quality were of a sufficiently high standard, then the load could be powered indefinitely. The batteries used were ordinary lead-acid batteries, and after 3 years of tests the batteries appeared to be in perfect condition. Their tests revealed a number of very interesting things. If the circuit was switched off and the batteries discharged to a low level, then when the circuit was switched on again, the batteries returned to a full charge in under 1 minute. No heating occurred in the batteries in spite of the massive charging rate. If the circuit was switched off and heavy current drawn from the batteries, then heat would be generated, which is quite normal for battery discharging. The system operated lights, heaters, television sets, small motors, and a 30 horsepower electric motor. If left undisturbed with the circuit running, then each battery would charge up to nearly 36 volts with no apparent ill effects. Control circuitry was developed to prevent this overcharging. These test results show spectacular battery charging and battery performance quite outside the normal range associated with these ordinary lead-acid batteries. Are they being fed short, very sharp pulses? It would look as if they were not, but one very interesting piece of information coming from Electrodyne is that the circuit did not operate correctly if the switching rate was less than 100 cycles per second. That is 100 switchings in 1 second. The Electrodyne switching was done mechanically via 3 discs mounted on the shaft of a small motor. One other detail reported by the Electrodyne testers is that if the switching speed exceeded 800 times per second, then that was dangerous. But unfortunately, they didn't say why or how it was dangerous. It clearly was not a major problem with the batteries, as they were reported to be in good shape after 3 years of testing. So definitely no exploding batteries there. It could well be as simple a thing as the voltage on each battery rose so high that it exceeded the voltage specifications of the circuit components, or the loads being powered, which is a distinct possibility. It is possible that at more than 800 pulses per second, the charging produced excessive cooling, which was not good for the batteries. It's generally accepted that for a circuit of this nature to work properly, the switching has to be very sudden when switching on, and even more so when switching off. The Electrodyne Corporation staff used 3 identical discs mounted on the shaft of a motor as shown above. This allows the contact brushes to be located on opposite sides of the discs. There are of course many possible alternative constructions, and I've been asked to show how I would choose to build this type of mechanical switching. The common idea of using mechanical relays is not very practical. Firstly, relays have trouble switching at the speed suggested for this circuit. Secondly, with a contact life of say 2 million, as is normally claimed, and switching speeds are just 100 times per second, the relays would reach their projected lifespan after 2 weeks of operation, which is not a very practical option. The objective is to have a simple construction which produces several switchings for each revolution of the motor, easy adjustment of the timing of 2 separate sets of 3 switches, one set being off while the other set being on, a construction which can be taken apart and then assembled again without altering the timing, and an electrical connection method which is straightforward. Obviously, the construction needs to be to use components which are readily available locally, and ideally only require simple hand tools for the construction. This suggested construction allows adjustment of the timing for both the start of the first set of switches and the start of the second set of switches. It should be also possible to introduce a short gap between the operation of these two sets of switches. This particular design is assuming a gap between each switching operation, as that may be beneficial. The switch contacts are rigid arms pulled against the rotating drum by springs. The contacts touching the drum can be of various types, and the ones shown are brass or copper cheesehead screws or bolts, which are particularly convenient, as they allow standard solder tags to be used to make the electrical connections to the switch wires, which then run across to ordinary electrical screw connectors, all of which can be accessed from above. I would suggest that 4 screw connectors should be used as a block, as that allows them to be fastened in position with 2 screws, which then stops them rotating when the wires are being tightened. There should not be any need for the conducting inserts in the switching cylinder to be particularly wide in the direction of rotation. So a practical construction method could be as is shown here. This diagram shows the arrangement for the device seen from above. You have an axle running all the length of this part here, and an identical arrangement on the other side. The arms on this side are coming down on the drum for the top. The arms on the other side are coming up on the drum from underneath. And you've got a conducting strip, a gap, a conducting strip, a gap, and a conducting strip all the way around the general shaft, which is driven by a motor and supported in a ball bearing at the other end. And that's the way it looks from the top. From the side you can see the upper arms are being pulled down by a spring, which allows you to set whatever strength of press against the drum that you choose to use. The same applies on the other side. You've got a spring pulling the underneath arm up so that it touches the drum disc itself. Now the thing is, when the contact at the top is made, the contact at the bottom is not made. These general central pieces are held up by angle brackets on an ordinary baseboard. The contact arms are shown as attached to each other in pairs. A lower level of construction accuracy can be allowed if they are all kept separate and a spring used for each arm rather than one spring for 2 arms as shown in the drawing. I strongly recommend that the switching drum be solid and the brass or copper insets be a fair thickness and keyed securely into the drum. The surface of the insert should be very gently eased into exact alignment with the surface of the drum, possibly by the very careful use of a small file or lathe if you are lucky enough to have access to one. The pivots for all of the switching arms can be a length of threaded rod with lock nuts at each end. There should be almost no movement of the switching arms when the drum is spinning, so no enormous precision is needed for the holes in the switching arms through which the threaded rod runs. Having said that, it must be understood that each switch in the set of 3 must turn on and off at exactly the same time, so the contacts in the spring-loaded arms must slide on to and off the conducting strips in the switching cylinder at exactly the same time. The drawing shows 3 conducting inserts at each of 8 evenly spaced positions around the circumference of the drum. The number around the drum is not critical. although this suggestion gives 8 switchings per revolution. If you choose to use a different number, you need to remember that the positioning of the arms underneath the drum will be different. You need to arrange it so that just one set runs off its conducting strips, that the other set is on the insulating section of the drum body on the other side. Both sets of switches must not be on at the same time, as that short circuits the batteries, which is probably not a good idea. The timing adjustment is achieved by moving the supporting block slightly, by easing the 4 clamping screws and sliding the block to a more convenient position and tightening the screws again. This of course is done when the drum is not rotating. Each set of 6 switching arms needs to have all of the arms exactly the same length between the sliding contact, shown as a bolt head, and the pivot hole. Each of the conducting strips inserted into the drum need to be aligned exactly and be exactly the same width. Otherwise the switching action will be ragged and not properly synchronized. The supports for the switching arms can be either a single block with slots cut in it, or the easier construction shown, where it is fabricated from several standard rectangular pieces and glued or screwed together. The unequal amount of conducting strip compared to the non-conducting part means that there will be a timing gap between each pair of on-off switchings. In spite of that, the battery switching will be a 50% duty cycle as required. The switching sequence will then be on, off, pause, on, off, pause, on, off, pause, and that may well be a desirable arrangement, as having an interpulse delay can be very good for battery charging. However, please don't imagine that the Tesla switch described here is a plug-and-play device which you can switch on and it will give you the sort of outputs mentioned above, as that is very much not the case. You need to see the Tesla switch as being a long-term development project with high potential. If you use the Tesla switch circuit with manual switches and run each phase for many minutes before altering the switching, it can give up to 4 times better performance than running the load off the 4 batteries in parallel. That is not what the Tesla switch is all about. The Tesla switch is one of the more difficult devices to get operational, in spite of the fact that it appeals to a large number of people. There are 3 possible modes of operation. If the diodes are turned the wrong way round so that they can feed current from each battery, then the operation will definitely be a coefficient of performance less than 1. But it will be a good deal better than operating without the switch circuit in place. The second way has only been achieved by John Bedini as far as I'm aware, and that is where the circuitry is the same, but the circuit components and connecting wires are adjusted very carefully to produce circuit resonance. When that happens, the circuit becomes self-powering, although there's little or no extra power for other devices. The third way was developed and tested over 3 years by the staff of the Electrodyne Corporation in America. In this version, the diodes are reversed and they only feed sharp voltage spikes back to the batteries through the diodes, which supposedly don't allow current to flow in that direction. This is a very different form of operation, where the operating power flows into the circuit from the local environment. The batteries need to be conditioned through long periods of being operated this way, as the cold electricity used in the circuit is the opposite of hot electricity, which the batteries have been using up to now. The long conditioning period is generally enough to make the average builder give up and believe that the circuit just doesn't work. Dave Lawton was faced with exactly the same type of problem when he attempted to replicate Stan Mayer's water fuel cell. It appeared dead and produced nothing during a whole month of testing, and then it suddenly burst into life, producing large amounts of HHO gas for almost no electrical input. Without his exceptional patience, Dave would never have succeeded. I believe that the same applies to the Tesla switch when wired correctly with the diodes blocking current from the batteries. It's likely to take a long time and patient testing before the system swings into life. One experimenter who did not believe that the diodes could possibly work that way round tested the arrangement and discovered that in spite of the theory, in practice, the reversed biased diodes actually pass very sharp voltage spikes to the batteries.